Uh, all right, thank you very much. So I'm Bernardo. I'm a postdoc at the Academia Sinica in Taiwan. Um, so I'm here to talk about the backreaction of scalar field modes on an inflationary era through somewhat non-canonical method that is referred to as a classical quantum correspondence. So I would love to hear comments from you guys about this. I am admittedly not an expert in Q15 curved space-time, but I had the time to wrap up this little side project of mine in a paper last year. And here's our archive number and the paper. You can find it in EPJC. Let's do this. So my outline is as follows. I would talk about one motivation for considering backreaction, and then give a brief review. What do I mean here by classical quantum correspondence? Then jump to the gist of this result. Considering a scalar field on a cosmological background, and basically tackling how the expanding background is going to respond to the presence of the scalar field particles that it creates itself. I would compare to of course, the results would have to rely on this methodology, and we will always question how reliable is this methodology. So I would compare it with a canonical approach, which is considering the perturbative-iterative method, the ones we're familiar with in the semi-classical gravity textbooks. The universe is expanding, all right? So extrapolating from the observations we have nearby, then to the early universe, there is a period there that we refer to as inflation, and it's a period of accelerated expansion. And in the context of a QFT curved space-time, it is practically a quantum mechanical factory of particles that can be drawn out of the vacuum. So the particles it creates should, of course, eventually accumulate, and this would we speculate that these are the same ones that they would freeze when they get out of the horizon, and they would re-enter right about the radiation era. Then this would be the source of the inhomogeneities that we see also today. The question that I would like to tackle, however, is when suppose we have driven enough of these particles out of the vacuum, then how should the space-time respond to that? I mentioned that the space-time would be accelerating, and this is the content of our gravitational equations. And in one of the most beautiful words that capture this is by John Wheeler, when he said, space-time tells matter how to move, and then matter tells space-time how to curve. So then matter should also influence an accelerating expansion, despite how small it is. Of course, it matters how small it is. And then during the inflation, so we are always on a concrete context. I would tackle the problem during inflation. So particles are drawn out of the vacuum, but so the backreaction question is, how should the expansion respond to the presence of the particles? And the canonical way that we can do that is to first get the energy density of the particles drawn out of the vacuum, and we know this from the semi-classical approach. Just fix the classical background, and then calculate the particles that you can draw there. Then you create this energy momentum tensor from these created particles, and put this back into the Einstein equations, and see what how the space-time is going to respond to these created particles. Yeah, so now that I've mentioned that motivation, let me draw you to this apparently new method of classical quantum correspondence. So first, it's not about making the terminology is can be quite confusing. It's not about quantum particles being stretched to their classical to classical objects by means of the expansion, but rather it is an exact correspondence between the quantum harmonic oscillator and a complexified classical harmonic oscillators. So just two classical harmonic oscillators. It's one complexified version of that. So this classical quantum correspondence is a way to treat the backreaction. It's been around since 2018, and it's practically just the same as, it's similar in spirit to the Bogoliubov coefficients. And in fact, there is an exact translation from that to the classical quantum correspondence that is expounded in this seminal work. Anyway, the main idea is like this. So the quantum harmonic oscillator, we can see the operators relevant to us in the left side. There's the Hamiltonian, the quantum harmonic oscillator, and then this is the creation operator, and it's a function of time, because in this context we consider the background as coming as driving this frequency, which is time dependent right there. So of course we are all familiar with the case when the frequency appearing here is just constant, then we get the usual creation annihilation operators. We can calculate everything. However, when the frequency is changing, and then the operators would change as well, but we can expand about a particular basis. Then we get the idea of particle creation from a classical background. And the Hamiltonian, for example, would be given by the vacuum expectation value, for example, would be given here below. All of these equations apparently can be translated to classical oscillators, and they would seem to be independent if we look at their equations right here. So we have classical oscillators here, Xi and Chi. Anyway, just the main important thing here is that the initial conditions of these classical oscillators are constrained. So one cannot, in the sense that when one is moving, just imagine the initial conditions right there. So we have two classical oscillators. The one starts from rest, pulled from the what do you call this, equilibrium position. The other one, you start from the origin, but you push it to the left. They're out of phase by pi over 2 if my arithmetic is right. This is a way to be able to calculate the vacuum expectation value of the Hamiltonian, for example, as well. In which case, apparently one can write down this in terms of just the energy sum of the classical harmonic oscillators. And since we got easier ways of dealing with the classical harmonic oscillator than with quantum operators. I mean, it's tricky to solve quantum operators because we got to solve operator equations of motion and stuff related to the fuzziness of quantum variables. But if you can deal with them by using classical oscillators, I thought it was nice. And then I looked for a way to apply this classical quantum correspondence to a space-time background, which apparently hasn't been done yet when I read the paper way back. So this is just review of the result of the CQC. But anyway, we can expect this from what we've heard so far. So in the classical vacuum, for example, just imagine the apple falling here in free fall. Then there's a linear potential that is provided by a uniform gravitational field. So the classical background here is that uniform gravitational field, and in a classical vacuum, no particles at all, then the acceleration of the background is going to be a constant. However, in the presence of virtual particles now, and this was the problem tackled first when the CQC was introduced, it was shown you provide your background with these quantum particles, then your acceleration would still end up to be a constant, but it's going to be different value. It's going to be lower than that. And which is an an effect that we can perhaps expect since this quantum particles that are being drawn out by this linear potential would influence the background as well. We will find an analogy of that later in the context of an expanding space-time. And let me now draw you there. So you look for an application of this, and so we to be able to apply it, and this is something we're all familiar with. So to be able to apply the CQC, I had to find a problem in which there is a quantum harmonic oscillator, and we know where that is in inflation. So you consider the simplest case where I could apply it, and that is an Einstein Klein Gordon model, and I've just made the potential flat and just turned it to zero. And then consider the classical space-time in at the same time as with this quantum scalar field. So these are the equations of motion of this coupled scalar field and space-time model. So we know how to do this. Write down the instead of using this variable phi, which allows us to write down the simple form of the Klein-Gordon equation, a massless Klein-Gordon equation, if you wish. We can consider a single Fourier mode, and then consider this translation to a different set of variables, psi, and for the time coordinate, we can use the conformal time. In which case, then we can we will be able to write down the equation for the Fourier modes of this Klein-Gordon field as given by this, and that's something that we can easily all recognize as a quantum harmonic oscillator, and where the driving frequency is provided by the expansion of the space-time. So the primes are time derivatives with respect to the conformal time. So then, while now being able to write that down, I don't think I've written the Hamiltonian in the slides, but you can find everything in the paper. Anyway, we can start then now talking about the quantum harmonic oscillator in the context of this of the modes of the field in an expanding space-time. All right, so let me just draw you to the results there. So I would break down the results thinking of this mode per mode, and by and they're relative to some threshold wavelength. So we're going to see the difference relative to that. So this first one is, so everything here is generated using the classical quantum correspondence. So this slide here is showing the results for what I am referring to as the super-Planckian modes, which are practically just meaning the wavelengths greater than some Planckian value of the wavelength. So it's not the Planck wavelength, but it's of the order of the Planck wavelength, ones that you can construct with the physical constants, the fundamental constants that we have. Anyway, this is showing the scale factor and then the energy density of the scalar, and we can see here that so what the K is the wave numbers, so increasing wave numbers, decreasing the wavelength. So as I am increasing the wavelengths, approaching much larger values of the smaller values of the wavelength, we can see that the scale factor would tend to decrease even more. And I have the Hubble function in extra slides showing that the Hubble constant is the Hubble function is actually approaching a constant, and then they're going to lower the values. But if you want to see that, we can talk about that later. The energy density of the scalar is dropping due to the inflationary expansion, despite they being created out of the vacuum. All right. So this is for this we may perhaps expect. So this is accounting the back reaction of the scalar field modes on the expanding background, and the equation of state of the particles created here are 1, so they're not expected. No, I would not expect them to source an accelerating expansion. Rather they're going to decrease that as they are being created. Then we're seeing the effect here. Near Planckian modes. Now, as I tend to increase further, there's a wavelength, so some short wavelength threshold. Apparently, when you drop there, then you draw away from an exponential expansion. Your scale factor stops from transitioning to this accelerated exponential expansion. Rather, this continues to collapse to a 0 value. And this is indicating the presence of this Planckian threshold, which is why I'm singling out this lambda Planck bar. But with some value between 5.77, 5.78 in this Planck units I'm considering. Anyway, the energy density, as you can see, it's no longer just going to drop continuously. Because it's an energy density, and when the scale factor stops from, say, the accelerating expansion going to this collapsing phase, you can see that the energy density there, the scalar field energy density starts to actually increase. The other side of this is the sub-Planckian modes, as what I referred to them. Here, I'm considering the wavelengths which are shorter than what I have found to be the threshold wavelength, and for which case, in all of these cases, I would find that the expansion would always collapse. And I forgot to mention, sorry, my initial conditions here are that everything is starting from a classical de Sitter background. So I'm considering well, what's happening at the time is equal to 0 is the de Sitter expansion. Later I'm going to see I'm going to show you the comparison with the semi-classical case, where we just want one iteration and 2 iterations, the leading order, the next to leading order base. Anyway, this is what happens with the sub-Planckian modes. And now that the space-time is collapsing and everything's just collapsing together, the energy density is increasing, or the scalar field is increasing, as we can see right here in this right plot. Okay, I should wrap up soon. So just an analogy with the apple falling earlier in a uniform gravitational field. There, if you recall, the result was that the acceleration was renormalized. So in this context of the inflationary background, because it's drawn particles out of this vacuum, and the particles equation of state are supposed to be they're not going to source an accelerating expansion there. The equation of state is 1 for I fixed that because I just wanted things to be simple right now. The result was that so without that, the Hubble function is just going to be this starting point I considered. In the presence of a quantum vacuum, this modes of the quantum harmonic oscillator, the Hubble function is going to instead be something else, which is smaller, always smaller than its value without the backreaction of the modes. And the thing I got to emphasize here is that the backreaction of the modes were considered using the classical quantum correspondence, and it doesn't, as far as the algorithm goes, doesn't actually have any approximations. It is an exact correspondence from a quantum harmonic oscillator to the classical ones. The approximations come in terms of the modeling that I'm considering. I'll talk about that in my last slide. So here I am comparing the result with the classical quantum correspondence with the traditional iterative perturbative method, and you can see here by classical here, this is what we would get in our usual semi-classical approach, just keeping the backgrounds fixed. So these are the initial conditions that I have considered in all of those simulations. So keeping the this is for super Planckian mode. Anyway, so by leading order, it's a fixed background, and you draw the particles out of vacuum, then you calculate the stress energy tensor, then put it back into the Einstein equation. Then that's the LO for NL, and the next to the leading order, you do that twice. And the plot here, the inset is showing the percent difference between the next to leading order and the classical quantum correspondence, and it's not the most impressive thing, but it's not bad. If you can go up to the highest is at point, so it's sub% agreement between the CQC and our traditional method. As far as the energy density performs much worse, you can go up to 15%, but it's not still not too bad, I would say. I can increase the number. I've increased just played around with the number of iterations to 10.
Sorry,
then
we're a bit out of time, so if you can quickly.
Yeah, I'll finish in a minute.
Thank you.
Yeah, that's okay. Okay, with just 10 iterations, I was able to just see to go and drop the agreement to really sub% precision right here. If anyone's interested, please look at the paper and don't hesitate to email me about it. So that's it. So I'll skip the upper portion, but about the approximations I've made. This is considering just a single Fourier mode of the quantum field. So I don't know yet how to use the classical quantum correspondence in the context of because the real quantum. In real physics, of course, we always find not just single mode, the superposition of them. So with that being said, I haven't considered the renormalization of the fields as well. So of course, we know from just bare flat space and quantum field theory that if you add all of these modes, that's another problem that is going to require renormalization and regularization. I haven't dealt with that, so it's just considering one mode and just checking how is the space-time going to respond to that. To support the inflation, I consider just a bare lambda here. So it's not. It's also not the most faithful inflationary model that we have so far, which we know should be supplied by the inflaton. She should have some slight time dependence, going from a somewhat flat potential and dropping. Then, but it just needed something in my algorithm to support the initial inflationary expansion so far. All right, I'm stopping here and just perhaps just leave my extra slides here for the Hubble function.
Thank you, Reginald. We don't have time for questions because we are a bit out of time, but
okay, yeah, that's okay.
The conversation on Slack if it's not a problem.